What are you getting over there, Mike? Does it look like this?
Yes.
But it should, I don't know if I have the latest version. I hope I do.
Oh, no, so, well, okay, so on the, so I'm actually seeing your desktop. So the go-to meeting shows your desktop.
Is there some way to do it differently? So I can't use notes. So how do we do that? Let's just mirror
in
that.
the screen if there is a.
Excuse me, I want to fix something actually.
Yeah.
We can go into editing mode, just like regular mode. How do you do
Or
that?
the business. Yeah, I think because it's still things are on the PowerPoint. Escape now.
Okay, now how can I mirror so we're all just looking at the slides?
Just F5.
F5 and then what?
I think that should have to start.
What about function F5?
Yeah. But
No,
this supposed to-
That's not right. That's not right. You ever use this, Mike?
Not yet, no. I mean, if you just, what's present online?
Yeah.
That's a different service.
Okay, so you just want to mirror the displays might be a little easier.
That's what I was saying.
Windows, yeah.
I don't know, did everybody get the notes? All of you got that by email?
Did you send me something by email?
I thought you were copied, but maybe not.
I didn't see it.
So we're going to follow the notes kind of closely, but maybe try to find some more time for discussion so we can go through it point by point. And the idea in the first segment today, tomorrow, is to talk about orientation-dependent interactions and mathematical description for them. That's where we're headed. And the motivation comes from lots of NMR experiments in solution in solid state. So the situation, solution in solid state, you can talk about similarities and then you can talk about contrasts. Similarities, there's a lot of similarity. One thing is, we've been working in a paradigm where we have an initial density matrix or an initial product operator describing our spins. And we have a Hamiltonian, and the job that we're focused on is to figure out what the spin will look like at a later time. Well, it's the same thing. It's all a solution. General goal, the kind of information that you'd have going in. And even some of the tricks, even some of the simplifications and tricks, so-called truncation, interacting frame, going into a frame where you make the pulse disappear or the applied field disappear. Some of these things are quite parallel, quite similar. But where the big difference tends to come up is about the anisotropy, the orientation dependence of every coupling and every shift. Now, there again, you could say, thank you so much. Thank you, Roman. Thank you. You could say that this orientation dependence has some. Mike, do you have any advice for me in terms of that eyeball there and where I should stand and how I should move around or not?
So the screen is, if you walk all the way over to the screen, it'd be covered, and all the way essentially almost to your water bottle, so you're all fine in there. Even if you stand there, I have you in frame.
Thank you, Mike. Thank you so much. So the fact that there's orientation dependence does affect the two kind of modes of NMR, but it affects them a little bit differently. And in solids, one of the examples that we're going to work towards having a quantitative description of is magic angle spinning. We want to derive the equations for magic angle spinning and discuss them a little bit. In liquids, a typical application is to organize a sample so that it has a preferred orientation, a very weakly preferred. Maybe less than 1% preference to be with its long axis parallel to the B field versus its long axis parallel to, or is sitting in a plane orthogonal to the B field. That's just an example. So the alignment could have different geometries, but the idea is that it's a very weak preference. And then in an experiment like that, where there's any sort of preference in orientation of the sample, you'll have explicit consequences of orientation-dependent interactions. The anisotropy affects almost every experiment by which we probe dynamics. That's not the first thing we're going to talk about. That will be sort of in the second half of the class. Relaxation, chemical exchange in principle. But here again, it's a little different, solids versus solution. And then there's one extremely important orientation-dependent interaction, the dipole coupling, that gives us arguably our strongest constraints on structure from NMR. And there are many things about that interaction, the dipole interaction, that we'll want to be able to treat quantitatively for both solids and solution. So these are some of the motivating considerations. What is it about NMR that means we want to deal with the equations for anisotropy? These are some of the experiments, okay? I asked some of you last week, had you been using spherical tensors? And almost everybody said no. And then I asked, do you have some access to Mathematica and MATLAB? Because maybe we can do some practical equations and things like that. And maybe we'll have a couple of workshops for using different kinds of software like we did last week. We organized for you last week. So people said some yes, some no. So let me know if you have a different answer to that. Sitting here today, you have, I know some of you pretty well what your background is, but is this going to be new material for you if we talk about the spherical tensor notation, or it's old material that you're reviewing, or what's your feeling? It's new for you. And if we said, well, here's a homework problem that you can do on paper and pencil, but it might be a lot easier if you just type it up into MATLAB. Am I just making everything more complicated for you, or do you like that idea, or what's your reaction to that? You're not sure. You have to see it before you can answer me, right? So we'll think about that. We'll think about doing some of that. Now, a little bit of this I already said while we were trying to set up the projector, but let's go through it because I think it's a little more structured in the way I thought ahead to type it up. The main thing about solids versus solution, the way we define it as NMR spectroscopists, is whether or not there's overall tumbling, fast overall tumbling. And if there's no fast overall tumbling, then practically speaking, we're going to call that a solid. It's not the same definition of solid that a solid state physicist would use. It's just our definition. And in liquids, it's got to be actually fast. You know, a microsecond's not going to cut it. We want something that's low nanosecond to picosecond, and then you get beautiful spectrum, right? Now, if there's not any tumbling, then one of the experiments that people do a lot, and is the one we're going to talk about the most here, is to do magic angle spinning. And even if you don't really know what the magic angle is and why it's magic, don't worry about it, because that's what we're looking at. That's our target in this section. Now, when you do NMR experiments with magic angle spinning, then you don't expect any particular relationship between line width and molecular weight. They're not directly connected by any physics, and that's cool. Line width in the best case is not as good as the best case of solution, but the line width in the worst case is a pretty nice thing. A definite format of an experiment, besides magic angle spinning, is to take the sample and orient it. This is an experiment that's used to study membrane proteins, for example, in the labs of Opella, Cross, and other people in Cross in Florida. You get from that experiment very big effects plotting the chemical shift as a function of angle. It's not a few ppm. It's, you know, like 100 ppm. It's the full range of the normal spectral width in some cases. Depends on the functional group. So those are big opportunities. If you can orient your sample differently and you can see a shift that's large, it could be a very sensitive way to probe structure. Now, a lot of the time we study what we call powders, and here again we have a kind of specialized use of that word powders. What it means is that the sample is static, it's not dissolved, it's not tumbling, or solid, the way we defined solid before. But it's not oriented at all. It's like completely random. So maybe an example would be a crushed crystal, very small crushed crystal, and shake it well and make sure that every crystal is randomly oriented. So you represent all possible orientations. And a histogram in an ensemble, inhomogeneously broadened lines are expected. That's the kind of sample that's often studied with magic angle spinning. But instead of a crushed crystal, you might have a frozen solution of a protein of interest, or something that pelleted in the centrifuge, and you don't think that the centrifugation induced order, which is a question, for sure. So this is a magic angle spinning experiment, a typical format. This is the so-called static NMR typical format. For both of them, in the spin physics, the distinguishing feature compared with solution NMR are the networks of very strong dipole through space dipole couplings. It's not just one coupling. So when we do the math today and next time, we're going to be talking about an isolated coupling. Beautiful, symmetric equations, lots of nice conclusions, but the reality, and most of the samples that we study for proteins, is not one coupling. It's a network. And it may not even be an isolated cluster. It might be a quasi-infinite network. That's where the complications come in. And we end up wanting to remove those couplings from most of our experiments. And that's where the solution experiments have this advantage, that the tumbling is removing those networks of couplings without you doing anything. With solids, we're going to have to do something in our experimental format to bring pseudo infinite networks, strong couplings under control. And by the way, when I say strong, we have a tendency, I think all of us in the instructors have a tendency to say fast, slow, strong, weak. And it's important to always remind you what the values are, so you start to get a feeling for the order of magnitude. When I say these dipole couplings, network, nearly infinite network of dipole couplings in solids are strong couplings. Let's talk about some numerical values. 30 kilohertz or so for geminal protons, and nearly the same value for vicinal or tertiary contacts. 30 kilohertz. I should compare that to tens of hertz, up to 100 hertz for J couplings, depending on if it would be geminal, vicinal, and so on. 10 to 100 hertz. Single bond, double bond. So it's a different order of magnitude. It's 3 orders of magnitude bigger. So the whole behavior will probably be qualitatively different. I mean, we know for a fact that it's qualitatively different. And if sometimes our goal for solids NMR is just to get rid of that whole network of dipole couplings so we can study something else, so we can get control of the magnetization in a pulse sequence, what does it take to get rid of a network of 30 kilohertz couplings? Well, people are trying to figure that out in terms of magic angle spinning, asking questions like, is 60 kilohertz spinning enough? 60 kilohertz and you're down to a rotor that contains about a microliter. Is 100 kilohertz enough? So these are ongoing experiments in leading labs around the world. thinking about just how fast you have to spin in order to remove a network of couplings like that. And then dipolar couplings could also be removed, of course, by decoupling pulses. Does that have to be 200 kilohertz? How big does that have to be? And for the most part, we live in a time where it's almost in reach experimentally for most of us. We're not quite getting rid of those couplings. So every experiment that we talk about, if you just feel like it helps you to stay awake to ask a question, most of us, that's true. If you just listen and you don't talk to me, you might start to fall asleep with all the equipment. Here's a question you can always ask. Do you need to use some isotopes to get rid of some couplings to make it work better? How are those networks of couplings affecting this experiment? It's always a good question for solids NMR. So that's a big difference, solids versus solution, and it drives all the differences and choices of hardware, those strong coupling networks. But as we said at the very beginning, while we were having these projection problems, there's so much that's in common, though, between solution and solid. So I just highlighted the differences, but remember at the beginning I said, and what Art's been talking about for solution NMR, we could state in the biggest terms what's our goal. Our goal is to understand coherent evolution, the effects of pulse sequences. Somebody tells you what your starting magnetization is, what the Hamiltonian is. The skill you should leave this course with is you could predict the future. And you use tools like the density matrix. Hamiltonians are simplified with truncation. You use product operators, you use frame transformations. Those are the things you do to simplify it until the math is easy enough for mere mortals like ourselves. And that's all very similar between solids and solution. It's slightly more complicated, but it's not that much more complicated. And there's a lot of similarities also in the treatment for relaxation and chemical exchange. We use the Redfield theory for both cases. We use Bloch-McConnell equation. We use stochastically developed. These famous equations, they're used for both. So keep in mind that we're not starting over. We're going to use pretty much everything that Art talked about. And in a broader sense, in terms of practitioners in the field and what's exciting these days and what are we battling, both of us, both communities are battling line width and sensitivity so that we can move on to the most exciting biological systems. And so there's so many parallels, and we're not starting over. We're adding a piece, and the piece is the orientation dependence of all the interactions. So what do we do? Here's my outline for today and probably part of tomorrow too. First, I'm going to give you some examples, just figures from papers where anisotropy was the main feature that's being discussed. Then I'm going to start to talk about the math that you use to describe anisotropic interactions, and it's a bunch of rotations. And so we have to talk about why, what are we rotating, why are we rotating, how are we rotating, what does the equation look like, and we'll take our time. I'm not going to move forward if it seems like people are now following it, so we'll start wherever we're at. Once we get comfortable with describing the rotation of molecules that have anisotropic interactions, then we'll start to put together some Hamiltonians that describe experiments. And some of the things that happen with that frame transformation, we talk about a coordinate frame tied to the molecule and a coordinate frame tied to the magnet and how you move from one frame to another. And we'll talk about, this is maybe the biggest thing, if you all haven't done this before, the spherical harmonic notation, maybe that'll be the biggest takeaway for you, and I think our plans to use it. So if it sounds a little detail-oriented and you think you'll snooze through it, I'm just warning you that I think Art plans to use it for the rest of the term, okay, these spherical tensors. And I'm trying to convince you they're not that complicated, it's not that bad. They really save you a lot of effort. And then once we have that notation down, we'll make our work so much easier that we can start to do complex pulse sequences. So that's sort of the flow of the lecture, okay? Does that make sense? Anybody have questions about anything before we get going? Now, the next segment, which if I was going to rush you guys would be tomorrow, but it'll more likely we'll start at the end of tomorrow and go on to next week, is our target is to have you follow the math for the magic angle spinning experiment. It's just an example for those of you who do solution, but it's the main thing for those of you who do solids. So I always pick that as my first example, just mathematically, how do you describe the mathematics of magic angle spin? And then we have a few other pulse sequences. What I'm hoping is that when we do the pulse sequences, we'll read a few things from the primary literature. So it would help you pick up another pulse sequence paper and be able to read it after we do one together. Now here's some optional topics. And I am putting this up now because I'm always up for input. Input could be correcting my math, and could be asking for a new topic, asking me to cancel a topic. I'm very flexible in that respect for the most part. So I expect we'll have a special topic on proton detection and deuteration, and that's because of a visitor who's really led the world in that, and he happens to be here in New York City, and he agreed to teach a class. But it's off sequence. It's off sequence. It's going to be on Monday. So we're going to send you an email about that. That's the one it's the same thing I announced a week ago in class. I usually like to cover effects of motion, fast limit motion, slow exchange, relaxation. And if I do that, it's probably going to be after some more lectures by Art, so probably be later in the term. Something we never covered here, but I like to cover, if there are people here who are particularly interested, is paramagnetic systems. What does a solid state NMR look like? Dynamic nuclear polarization, signal enhancement techniques. We could have a lecture or two on that if we want to do that. In the past, sometimes I covered the deuterium direct detect spectroscopy. I'd like to cover simulation strategies, like computer programs, where you can put in a pulse sequence and have it make the prediction for you. That's going to be a little bit after the term ends, so it won't be a formal part of the coursework, but we'll have a little workshop because the guy who developed a really lovely package for doing that kind of stuff also happens to be willing to come to New York just to teach you. So we have two distinguished visitors that I've lined up for you, in addition to Bruce. This is a topic students often ask for. We maybe do a little half a lecture on. It's just sort of the workflow for assigning a protein. So these are choices. This is a menu, and the only thing that is almost decided already is that I will have these two topics, but they're not really going to influence your grade. So if you're not here, don't worry about it in terms of the fact that this is a course. The rest of it is just, if you request it, we'll do it. Otherwise, probably not. Okay. So I like to say a little bit about, as we get started, assumptions. If you see me using something in the way of math or whatever that you haven't seen before, I'm hoping this is going to be a space where people are honest with each other and will raise their hand and we say, I don't know what e to the ix is or whatever it is, okay? I don't want this to be a place where we blow through and bluff and hope we're going to look it up later. So I'm kind of assuming that you remember how to multiply matrices, but even that, we can just stop and remind you. I think Art's been using Taylor's expansions. I think I'll be using it. If you don't remember it, it doesn't matter. If you've been bluffing up till now, it's okay. Just raise your hand and we'll go through it, okay? We might talk about diagonalizing a matrix. You may need to review that, or we can do it together. Some things that I'm not expecting you've done before, but we need to do is taking outer products, inner products of tensors. Maybe that's something you do all the time, maybe not. We'll introduce a special set of functions called Bechdell's functions. So there's some math that most people haven't done before, and there's other things we need to review. But please, as we go through this, be present, ask a question, etc. So here's a few examples, beginning with experimental examples. Something seems to be missing here because of the PC to Mac, and presumably it wasn't important. Chemical shielding. Chemical shielding is anisotropic. Pretty much all the interactions we talk about in NMR are anisotropic. But if you've been doing solution NMR, you just never noticed. J coupling's anisotropic, quadrupole coupling's anisotropic, bipole coupling, etc. Chemical shift. So as you know, chemical shift is a shift in these difference in the two levels when the only interactions are between the nucleus, the applied field, and the electronic structure context of the nucleus. And the idea is that the molecule has a susceptibility because the magnetic field perturbs the molecule, perturbs the orbitals in two ways, can actually change the details, the energy, the character of the orbitals ever so slightly. It can introduce a little mixing of excited states So something like a little bit of paramagnetism, a little bit of population of singly excited states. It can also induce precession within an orbital. So we usually think in terms of two kinds of perturbations of the magnetic field on the molecule. And it's not the easiest to do quantum chemical calculations on. It's not your beginner's quantum chemical calculation, because it's not a ground state property. It's an excited state property, and it was quite a achievement of the community to move these tools forward to where we can start to trust the trends that come out of quantum mechanics, where we can show that those trends agree with small molecule trends. So increasingly they do, with some caveats. And that tends to reinforce that our physical understanding of where these effects are coming from is probably on good footing. So those perturbations on the molecule can be thought of as introducing another local magnetic field. You can talk about susceptibility, like we talk about with bulk properties, like gooey balance and those kind of experiments, or you can talk about it very locally as introducing local magnetic fields. We'll probably talk about it mainly in the second way. So the total magnetic field could be the one you applied plus a little something extra that the molecule gave you. It's like a new magnetic field. There's no guarantee what direction this new magnetic field will be on. It can be in any of the Cartesian directions or any mixture. So response of a molecule depends on the symmetry of the molecule. And what we're mainly talking about here is it depends on the orientation of the molecule. So that, here's my nucleus. As I rotate the molecule, the nucleus will probably remain trained on B naught. The nucleus's main interaction is with the applied field. So picture that the molecule is rotating, and the nucleus is like a gimbal mount inside it, and it stays trained on the magnetic field. And as I rotate the molecule around it, it's going to change the local magnetic field. So as I rotate the molecule, I'm going to feel a little stronger local field, a little weaker, negative, positive. That's what we're going to describe mathematically in what we're about to do. Now, it's a first order effect. What I mean is the induced field is like a percentage of the applied field. It's linear. It's first order. Why? Because it's small, so we assume that. It's just a mathematical approximation. It doesn't have to be first order. That's not what necessarily comes out of a full-blown physics treatment. But we're going to treat it like it's first order and linear, which is very small, and it's a leading term. So it's like a derivative with respect to the external field, taking the leading term, and it's very, very small, very, very much smaller than 1. For a lot of what we develop, I'm going to stay with the chemical shift. But before I do that, I just want to mention that the other interaction we're going to be talking about, which is also anisotropic, is the coupling to a neighboring spin. And that neighboring spin casts a local field. This is through space. This has nothing to do with the bonding electrons in this case. The bonding electrons may affect it, but it would be very, very small effect we never talk about. So there are field lines that are cast by the nucleus, just like there would be if you had, one of those little horseshoe magnets. And they have curvature. They have a particular shape. It's a very famous shape, so we know how to calculate it. And it does mean that if I'm a neighbor spin, I'm going to have a different total magnetic field as I walk around in different directions with respect to the neighboring spin. Okay? So I'm going to be a probe spin, and there's an angular dependence with respect to my neighbor. We want the mathematics to describe that. We want to understand what are the circumstances that make all that average to 0, and anything else that we need to know about its spatial characteristics. So these anisotropic interactions have applications in biophysics when people align samples in a membrane and then align those membranes with respect to an applied field. I mentioned before the work of cross or Pella in particular, and here's a nice review article from NATO et al. 2009. So by using these anisotropic effects, they're able, if they got an assignment for a species, they're able to figure out if a particular amide may be pointing this way versus that way compared to the membrane normal. And if you get enough such information, you can begin to make a structure for that molecule. That's the idea. We talked about applied applications with partially aligned solution samples. So if a solution sample is not completely spherically averaged, it will have part of these couplings, CSA or dipolar, remaining. We talked about that a little bit. But most of what we're going to talk about, and we're going to develop the mathematics for, is an experiment in which you have a solid, that means again, no dissolving, no overall tumbling, might be in a membrane, might be an amyloid, might be a crystal, might be a frozen solution. It's not oriented. There's no orientation. And so it's randomly oriented in your sample holder. And now you take that sample holder and you put it in something we call a stator. Sample holder has special fittings, especially the end cap. And so if you blow air just right on it, it spins, and it spins very rapidly. We were speculating recently, maybe it's the most rapid mechanical rotation of anything that is made, maybe. But certainly, it's rotated up close to the speed of sound on the outside of the rotor. That's our limitation. And for the sizes of rotors that we build, you can calculate through that you have G-forces up to about 1 million. That's higher than a centrifuge, most of the centrifuges that we use. So that's the experiment, and now you've got a coil around that sample holder. So the air is blowing here to get it spinning, the coil's here, and a coil does NMR like usual, just like we talked about in solution, except that we tend to be interested in getting stronger pulses, pulses with a stronger viewer. But besides that, it's very similar. But you're spinning the whole time, and we're going to do the mathematics of what happens to the instantaneous frequency when you spin, and therefore what happens to the magnetization, and what happens to the spectrum. That's the mathematics we're going to do. Phenomenologically, you could think of the same functional groups measured in solution, measured in magic angle spinning, measured static. So what's going on with the static experiment? Why are the lines so broad? Why do they look like that? Please? Could be dipole interactions. Also, it looks like some CSA, doesn't it? But the thing is that they're not oriented, they're randomly oriented, so each orientation has a different frequency, and it builds up inhomogeneously like a histogram. And there's actually a lot of information in that, potentially, but it's so ill-resolved and so low sensitivity that you don't really want to study a protein exactly like that. But there is more information in those broad lines than in these narrow lines. People can interpret chemical shielding anisotropy. People can interpret dipole couplings and their mutual orientations. So in the end, you can think about some of the advanced experiments. We're looking to get that information with that resolution. Oftentimes, that's what we're trying to do. We want to know that this one was broader, this one was narrower. But in the end, we want to detect super narrow like that. So how could you do that? There was, for a little while, an experiment called stop and go, where you detect while you're spinning, and the indirect dimensions, you turn the spinner off. They were insane experiments in many ways, particularly having a desk down the hall from them, where the sound of the rotor spinning up and then crashing made it impossible to write papers. But there are more clever ways to do the same thing, to get the anisotropic information in an indirect dimension and the nice, sharp isotropic lines to assign. Another cartoon displaying the same thing, lovely animation from Donghua. So, the liquid, you ask the molecule to do the tumbling, solid state. We should draw a little molecule inside the rotor to make the idea completely clear. And what this says that the last slide didn't say is that the frequency of spinning is important. If it's low frequency, you get a comb. From one kind of spin, you get many peaks. But you always know that one of the peaks is at the isotropic shift, and then the spacing is the rotor frequency, so you know where to expect them. But from one site, you get many peaks. Still, it could be very informative. It's a strange result, but it could be very informative. We're going to derive all this kind of stuff. Well, I put it off as much as I could. Now the equations start. I want to talk about chemical shift and these local B fields. And now instead of talking in pictures and analogies and failed jokes and things like that, I'm going to talk in equations. So I need to calculate the induced magnetic field for the local environment of a molecule. And specifically what I'm interested in about it is how does it depend on the orientation of the molecule. That's my specific interest. And I said that we're all happy to assume that it's linear and small, that it does depend linearly on the applied field. So our Hamiltonian is going to have the Zeeman term. That's just if you would have a bare nucleus interacting with the applied field. And it's going to have this second term, which describes the susceptibility due to the molecular environment. This is the part that is going to be orientation dependent. If I took it out, it would be H gamma B I. B is a vector. B is a vector, probably written on the next slide, but it's a vector with three components, Bx, By, Bz. I is a vector. Oh, no, I'm sorry, it's right here. Bx, By, Bz, and it's a row vector. I is a vector of operators, spin operators. Measurement along x, measurement along y, measurement along z. So if I didn't have this thing sigma in between, it would be like the liquids Hamiltonian we already talked about. Bx Ix plus By Iy plus Bz Iz. And we only look at Bz Iz because magnetic fields that we use in the spectrometer are just along Z. By convention, that's our coordinate system. So then the solution example would be H bar minus H bar gamma Bz Iz. So it's the same equation, but we've plopped this thing in here, this thing called sigma. It's a tensor. It's a 3 by 3 tensor. And what it offers you is the answer to the question. If I put the magnetic field along B, Z, I put a field along Z for my molecule, and then I measure along Z, how much extra field do I have because of the orbitals? If I put the field along Z, but then I measure along Y, how much extra field do I have? Maybe I put the field along B, but the molecule has chirality, it has shape, so maybe it spits out a few extra fields along Y. If I put the field along Z, maybe the molecule can generate a small field along X. Keep going. If I put the field along Y, which we usually don't, but you might, what will I get as far as a molecular response, but along X, Y, and Z? And finally, the last piece. If I were to put a perturbing field along X, what fields will I generate along X, along Y, along Z? Those are 9 independent experiments. They don't, no 2 of those experiments or questions have to be the same as each other. It's 9 different questions. The field this way, this way, this way, measure this way, this way, this way. In most arbitrary situation of a very low symmetry molecule, it could be that they're all different. Up here, I've written a simplified expression. So the induced magnetic field could be said to be just this much, multiplying this vector by this tensor. All of that together gets you the induced field. B applied times sigma. And this simplification, moving from this equation to this equation, is simply saying, yeah, but we never use Bx and By, so let's set those 2 to 0. So it'll just be Bz, which we usually call B naught. Bz and B naught are synonymous. So B naught, if you think about how this multiplication will go, row, column, B naught will get multiplied by sigma 3, 1 to make the X component, it will get multiplied by sigma 3,2 to make the Y component, and it will get multiplied by sigma 3,3 to make the Z component. So given that we know we only have B naught along Z, we can say that we're only really interested in 3 elements from that tensor. The rest go unmeasured in this experiment. Any questions about that? About how it got multiplied, about what we're talking about? Any questions at all? So another way to think about all 9 of those tensors is that if the susceptibility is the ratio of the induced field to the applied field, then it's a matrix of 9 first derivatives. And we're going to talk about which pieces of that group of 9 numbers we really need and how they behave. But before we do a little bit more with those equations, I want to mention an analogy. So we're talking about, I put a field that perturbs a molecule, I can put it along Z, and maybe I'll get a molecular response along Z or X or Y. If I put the field along Y, maybe I'll get a response Z, X, or Y. This is a strong analogy to another problem some of you may have studied or not, which is about material science and the materials responses. If I put a pressure along Z, you know it might deform along X or Y. You know that. It's intuitive, and there are tensors that describe that. You need 9 numbers to describe that. Deformation, stress, strain. This is the same math. This is the same math as long as everything's linear. So we just talked about that by convention, the magnetic field is applied along Z. And therefore, B applied is 0, 0, B naught, and B induced is this triple. Okay, we just talked about that. As I'm giving you another chance to ask a question, we're going to use it that way from here on out, so I want you to be comfortable with it. And then I put these 2 cartoons to show you that whenever I say this, I always start pointing to the ceiling and the floor, but we know that we're starting to have a few magnets around this place that actually run this way too, right? Not our measuring magnets, but some other magnets. You can make the magnet go any way you want, but whichever way it goes, Z is a long magnetic, right? So long as Z. Now, this is another simplification because for today and for tomorrow, our goal is to predict instantaneous chemical shifts and then predict spectra. So the first simplification, that B naught is along Z, is exact, and it's just a convention. It's just a coordinate system convention. So there's nothing more to discuss about it. The next simplification, there's always something to debate about it. There's always something to discuss about it. Now, the induced field, so far, this is how far we got in the problem so far, it is along X, Y, and Z, the induced field. It's of order a few parts per million of the main field, maybe 100. If you're dealing with fluorine or some heavy metal, maybe 1,000. If you're dealing with carbon, maybe 100. If you're dealing with protons, maybe 10 parts per million. Just like the isotropic shift, similar order of magnitude, okay? What you're used to seeing in spectroscopy. So I'm going to talk about how we could now just ignore the fact that you're introducing X and Y fields. So in the applied field, we only have Z. In the molecular response, we have comparable sized induced fields along all 3 directions. That's just what comes out of assuming that it's a tensor like stress and strain. Just a direct consequence. These things don't have to be 0, and there's no reason they'd be any different order of magnitude than this one. Maybe for some special molecular orientations, but we're interested in the general expression. So they're all about the same size, but I'm going to ignore 2 of them and just keep the last one. Now, why am I doing that? Why would I ignore the fact that the molecule creates an X magnetic field and a Y magnetic field? So what we want to do is predict spectra today, right? That's our goal. Here's B naught along Z, right? And then here's our molecular response vectors. Can you see them? This is sigma 3,3 B naught, an extra low field, or minus sigma 3,3 B naught. It could, in principle, be in either direction. Actually, usually it will oppose the field more often than anything. So let me draw a vector in the opposite direction. And then I'm going to have a comparable size vector, sigma 3,2 B naught should be along Y. So we should go into the board like that. And a little tiny vector like this, sigma 3,1 B naught. Okay, so do those vectors make sense to you? This is a terrible drawing here, but it's supposed to show a vector going into the board. This is a vector opposing B naught, and this is a vector along the x-axis. Does that make sense? Does the drawing make sense? Can you see everything? So what I'm doing is I'm saying I want to make use of this term. That's what this slide says. And I want to just ignore these. Now, why am I doing that? For predicting spectra. The chemical shift in the Zeeman term, what's going to happen with our spin? We have these magnetic fields, and then what's the rest of the story? We're going to have these magnetic fields, and then what? The spin or the magnetic moment of the ensemble of nuclei is going to do what? I beg your pardon? Did you say split? It's going to split, and what else? It's going to precess around it. Remember that torque equation? Those are the two things that we're interested in, the splitting and the precession frequency, which turn out to be the same number. The splitting, if you express it as a frequency, and the precession frequency, wonderfully, are the same number. So, and what do they care about? Do they care about components of the field or the total field? Can the spin tell which of these things that I put on the board it is, or just the sum total? You have to add all those components to make a total field, and all the spin can field is the total instantaneous field, right? You just add the fields. They're all magnetic fields. You add them up. It's a vector sum. So what's going to happen if I add B naught, which is along Z, and a little tiny extra thing, which is along Z? If I add them, what do I do? If they're exactly opposite to each other, what do I do? It's pretty straightforward. It's not a trick question. It's just B naught. The magnitude is going to be along Z, Pat, but it will be B naught minus sigma 3,3 B naught, or maybe a better way to write that is it's along Z naught, and it's B naught times 1 minus sigma 3,3. Sigma 3,3 is unitless, so that's a good thing to add and subtract. Okay, that's fine. There's nothing complicated there. So I include that term, and the math is so easy, I shouldn't have wasted your time with it. Now what when I want to add something perpendicular? How do I add two vectors and they're perpendicular? You need to use some geometry and trigonometry, right? And if they're exactly perpendicular, it would look like this. This is the Z component. And I square that, and then I add this thing, squared, and then I add this thing, squared. And then I take the whole thing and take the square root. Does that look familiar? I'm just you know, doing the Pythagoras thing. So I'm just trying to calculate that. Now, when this is of order less than a part per thousand compared to this, that's when I can say, you know what? We have a lot of precision in NMR, but I don't think we have that precision. And you can do an example if you have some questions about that, or even if you don't. I think it's a good idea for you to take that home and say, what's she talking about? I'm going to take 600 megahertz, 30 kilohertz, 30 kilohertz, and I'm going to add them as a sum of squares. And her claim is that 600 megahertz even is the right answer. That those two 30 kilohertz just don't contribute. And check. I would like you to argue with me sometimes. That would be great. So that's what we're doing here. We're saying, you know what, these are so small compared to B naught that when I add them vectorially, they're gone. That kind of argument is usually what underlies truncation. Truncation means a simplification of a Hamiltonian that has the effect of removing things that are different to the strongest term. So removing selectively some of the weak terms. And there's different ways to go about it. You can think about whether they commute with the strongest term, which is one way that it's often done or taught or whatever. I like to think about a frame transformation where you make the big term, the action of the big term go away, and then you see how the little terms look like when you've made the big term go away. That's another way to think about how to simplify and truncate. This was a very simple geometric argument. It says that that term is perpendicular. We know what that means when it's in 3 space. We understand perpendicular when it's just x, y, and z. Pretty soon we're going to be using spherical harmonics, very complicated spin degrees of freedom like I, z, s, x, and things like that. And then this crisp concept of perpendicular will end up arguing with each other, so that might not work that well. But in general, it's a similar kind of thing, that if it's weak and perpendicular, that's not going to give you anything. To the precession frequency, the spectral frequency. Now, please remember from this discussion of truncation, it's going to come back and back in our section on solid state interval. We're going to talk about truncation several times. But please remember that what's true for calculating spectra might not be true for thinking about relaxation. Terms that we're allowed to throw away when we're trying to figure out what the precession frequency is, such as this orthogonal y or x term, they might be big drivers of relaxation. So what you're allowed to throw away depends on the question you're asking, okay? Like what about B1? B1 is orthogonal, and it's weak. It's about the same size as these CSA terms. It's probably 10 kilohertz or 100 kilohertz, your B1 field. But we don't throw it away. It's a really big deal. So B1 is about the same size as my cartoon. Let's say it's along X, okay? Here's my B1. B1, and it's maybe similar order of magnitude, maybe 20 kilohertz, maybe 10 kilohertz. And instead of being proportional to sigma 3,1, it has nothing to do with the molecule, but it has this cosine omega naught t x hat plus sine omega naught t y hat, and it's an oscillating field. Now, why don't we just go ahead and do the same thing with the B1 field and say, wow, that's weak. It's not even perpendicular. It's like not even parallel with B0. It's perpendicular. So I don't think we have to consider this.
Yeah, so I think it keeps hitting against your sweater or something. It's just, you know, when you slightly move, it's kind of getting flicked. I don't know.
So what do you guys think about that argument? Let's just get rid of B1. Because I said, this thing is small and perpendicular. I'm going to drop it, and we're never coming back to this, and we're not going to talk about it again. So I think as a group, we have to agree that this is reasonable what I'm doing, or it's not reasonable. Because everything after this is going to depend on assumptions like this. So am I allowed to get rid of anything that's weak and perpendicular? Because that's basically what B1 is. B1 is weak and perpendicular. Should I do that? We can just stop pulsing. It will really simplify things a lot. Any opinions about that? This is definitely something Art talked about. You can look back in your notes in his section of the that section of his book. Any question, any comment from you guys? There's something very special about B1 that doesn't happen to be true normally about this term from the chemical shielding. There's something very special, tailored, especially for you, about it. What is it? If you're going to set up and pulse in an NMR experiment, what's the first variable? You're going to pulse, you have lots of things to choose about what the properties of your pulse. What's the first thing that you want to choose? Very first thing to get your experiment off on a good start. Excuse me? The direction is important, but before that, I want to know something else. If I'm walking up to Mike is helping install a new machine, I'm all excited about the machine, and I say, I want to do an experiment. I haven't gotten to do an experiment in 30 years. I want to do an experiment. By the way, what? What's the question? Thank you. Yeah, what do you set up to pulse at? What's your probe tuned to, and what's the transmitter? Because I probably don't have as much patience as Mike, and I'm not willing to change it, so I'm going to use whatever he has. If he says he's got phosphorus, I'm going to do that. So this is oscillating, and it's oscillating resonantly. This is not oscillating. Or maybe it is oscillating, but it's not resonant. There's nothing we've done to ensure that it's resonant. And the important thing about it being resonant is that that B1 field, if the magnetization is precessing because of the Larmor frequency, that B1 field is going to be lockstep with the magnetization. They have a fixed relationship with respect to each other, and they can get a torque and keep it going. That's resonant. The CSA term, there's nothing about it that suggests to me that it's going to be resonant. The molecule may move, I might do magic angle spinning, but none of that's resonant. Okay? So we're getting rid of weak orthogonal fields when we don't think that they're going to be resonant. And it could be a mistake if it's near resonant and you didn't notice. So there'll be some gray zone in this. Like sometimes it's crisp, it's like that's resonant, that's not, and sometimes there's a gray zone and we can all argue about the gray zone. But for this class, I think we'll have pretty crisp examples. That's not resonant, that is resonant. So we're getting rid of these other two terms from the CSA because we have no reason to think they would ever be resonant. Now we have that really simple equation. Instead of the isotropic shift in solution, sigma iso, we'll be measuring sigma iso plus sigma 3,3 in terms of proportionality constant for B naught. Okay, so B naught for the solution NMR experiment is not just B naught IZ like the Zeeman term, but you get this other term that's B naught. That's just Zeeman. And if you're doing solution NMR, it might be gamma B naught sigma iso IZ. And then the third term that we're adding here for solids is, if it's anisotropic, you figure out what the shielding tensor's 3,3 value is. These are all operators, operator IZ. This is a scale because it's just a component of the vector B naught. So we need a arrow. So Zeeman, isotropic shielding, and a little extra if it's anisotropic. And when I rotate the molecule, what's going to be happening is the value for sigma 3,3 will change depending on orientation. Because this equation talks about X, Y, and Z in a laboratory frame, in a frame where, as I've said several times, Z means the axis of the magnet. Well, I had to make a decision how to place the molecule in the magnet. And if I pick up the molecule and make a different decision, I'll get a different 9 numbers. So it's this value of sigma 3,3 that is orientation dependent in particular. That's where the orientation dependence can come in. And that we want to know how to describe that in a useful way. If we have a description of the molecule, of its orientation, we want to calculate sigma 3,3. We want to a set of equations that do a good job of that. And all of that gets added to the Zeeman interaction and to the isotope. So we had 9 numbers, now we only need 1. But we need to learn how to write that number as a function of molecular orientation. This is restating the answer to the question I bothered you guys about for a few minutes. And this is me again saying, if I were you, if that question wasn't obvious and the answer wasn't obvious, I would go home and play with it a little bit. Sometimes in this class, I'll talk about assignments that are not homework to turn in. It's just for you. Like, think about it so you'll remember it. Down at the bottom, I say, give me an example of a weak orthogonal field that does matter. I think I already answered that. That's B1 because it's resonant. Or the fluctuations during dynamics because they drive relaxation. But we haven't studied that formally yet. We'll get to it. All right. So, the Hamiltonian, the energy from which you can get the frequency of precession can be written minus gamma. This is it shouldn't have a 0. This is the vector of magnetic fields in the laboratory. This is a vector containing the spin operators in the laboratory frame. And this is a tensor describing the response function of the molecule. 9 numbers that describe the response function of the molecule. And we're saying we can do all this calculation, but in fact we only need the 3,3 element. But I've introduced something here new. I've introduced the idea that the response function of the molecule will have natural coordinates, and it's not the lab frame. There's like, I want to talk now about Z being the high axis, high symmetry axis of the molecule or something like that. I want to describe it in molecular terms. I want to be able to publish it, and I want you to be able to use my numbers. That's not going to be in my magnets frame. That's ridiculous. It's going to be in a set of coordinates that are tied to the molecule. Like a common thing might be the most shielded is perpendicular to the aromatic plane, stuff like that. So there's another coordinate frame that we're going to want to be able to talk about, and that's tied to the molecule. So now we have 2 coordinate frames. And this slide has a comment at the top that says that the energy, the Hamiltonian, the frequencies, none of that is going to depend on the frame that I picked, PAS versus lab. This isn't like the funny rotating frame, non-inertial fake fields. This is just coordinates on the molecule, coordinates on the field. And energy is going to be the same energy no matter what frame I pick. So, but the vectors that represent the field, the angular momentum, the tensor, susceptibility, they all do depend on the frame. They're only well defined if I tell you what frame I'm in. So everything that goes into this equation, other than maybe gamma, has a frame that I need to remind myself to put as a subscript or a superscript. The final thing has no frame. It's the same answer. I can do the whole problem in lab frame, the whole problem in PAS, or this nifty thing that I'm showing here where the susceptibility is in its natural coordinates, PAS. The spin and the magnetic field are in their natural coordinates, the lab frame. And I can do that because I introduced these rotations that move these 2 vectors from the lab frame to the PAS. I'm going to rotate the vectors. So in reality, I like to think about IZ, IX, B0, etc. in the lab frame. But so that I can multiply it by a PAS that I got out of a paper that's in principal axis coordinates, I'm going to rotate those vectors into another frame. So this is where we start to remind ourselves how to rotate things. And then we talk about rotation for like 20 slides. Okay? So we're about to go into endless discussion of how to rotate things. And don't forget that the reason we're doing this is so that we can work with 2 frames of reference and move between the frames with confidence, that we know we're doing the right math when we go between one frame and another. So again, typically we know the dipole coupling or the chemical shielding values in the principal axis system, an axis system that's determined by bond vectors and things like that. We know what V and I mean in the lab frame. We need to move from one frame to another. And I'm beating a dead horse here by saying, I can do this. I can take minus gamma, B naught in the lab, sigma in the lab if I happen to know that somehow, and I in the lab, and that's a valid equation. Or I could do sigma in the principal axis system, which is something I probably could look up in some Jack's paper if I know how to read the paper. And then I'm going to need to be able to write B naught in that principal axis frame, which is kind of weird, and I naught in the principal axis frame. So I don't know exactly what that means right now at this point in the lecture, but it's a consistent equation at least because it's all in the same frame. Okay, we don't know how to do it, but it seems to make sense. But here's something I'm not going to do. I'm not going to pick up lab frame coordinates for half my equation and be multiplying that by something written in another frame. I won't be doing that because that doesn't make any sense. That's gibberish. Okay, does this make sense? So this Hamiltonian can be any frame, but I got to write the equation consistently all in one frame. So what I need to be able to do, these are vectors. I'm pretty sure I know how to rotate a vector. I did that like in middle school or something, high school. So what my game plan here is to take the vectors that represent the magnetic field or the spin degrees of freedom and rotate them into the PAS. So I'm going to need to know what are the angles that relate the PAS to the lab frame, somehow. Somebody's going to give me those angles. You'll have a homework set where I tell you, assume the angles are da-da. Maybe you used a goniometer. So you have angles to some crystallographically defined axes. In the beginning, it'll just be given to you like ad hoc, like this is your homework and it's 30 degrees. But in a real problem, you might have to think a little harder. So you have these vectors for V naught and I. You have a proposed set of angles for your principal axis system that describes how you picked up that molecule and placed it into the field. And all I'm going to do right now is to remind you how to rotate those vectors into a new frame. The big question is, how did you know the angles? We'll come back to that. So that we're sure we're not going to make any mistakes. We're going to take it down a notch, and then we'll build it back up again. This is the stuff that I hope makes everybody more comfortable to talk about an error if you see it on my slide, or to admit that you don't remember something. Here's a rotation that I think we all can appreciate and remember. I've got a vector, it's only in a plane. It's just a vector V. It has an X component and a Y component, all right? Here's V. Now I want to move V and rotate it through an angle, like it would be a clock hand moving. It's actually moving. Everybody's got a fixed coordinate system, and this vector is just going to rotate like the minute hand, okay? So how do you do that? Well, if you tell me the angle, I can do it for you because I know that there's a 2x2 matrix, R, and I multiply it by whatever V's initial coordinates are, Cartesian coordinates, and it'll give me the new coordinates. And what R is, you need to tell me the angle you want, and it has cosine theta on the diagonal, minus sine theta and sine theta. This probably looks familiar. But you might like to just take the example that V is an X vector. Okay, so V written in not polar, but Cartesian coordinates would be 1, 0. Okay, it's an X vector, like 3 o'clock. And you might want to rotate it by 90 degrees and make sure you get the right answer. So if you're going to rotate an X vector by 90 degrees, what are you supposed to get for an answer? Do you get it? Just take a minute and just do it with paper and pencil. I know you did this before, but we're going to do so much of this, I want you to be sure of what we're doing. Everybody know what we're doing here? Does that make sense? If it's 90 degrees, cosine will be 0, minus sine will be minus 1. And then the idea here is that V is a column vector that initially is 1, 0. So if I do that kind of rotation, that's a plus 90 clockwise on an X vector, I'm going to get row, column, 0, row, column, 1. That looks like an x vector. I'm sorry, a y vector. So I started with an x vector and I rotated it around clockwise and I got a y vector by just using that. And if it works for that case, it'll probably work for everything else. But if you just get a little unsure of yourself here, then just take another example. Now here's a funny thing I didn't remember when I was first started to do these problems for NMR. We're going to be working with column vectors and row vectors. So let's think about some vector u. It should have been in bold like the v, but got messed up. And u has some initial value, and I want to transform it by the same rotation. Just because it's a row vector, instead of being a column vector, it's a different operation. Okay? It's u times r inverse instead of r on v. It's just the way it behaves. Go home, take a couple of examples, and argue with me tomorrow if you don't like it. So these are so-called active rotations. What that r is representing is that I actually sat in a fixed coordinate system and moved my vector. That's an active rotation. In the last slide, we said we need a lot of rotations, but we didn't need active rotations. We need so-called passive rotations. That means the vector doesn't change anything. It's just the coordinate frame that's changing. We're moving things from one coordinate frame to another. And it turns out that if I'm talking about a passive rotation instead of an active rotation, I can put a direct substitution. Either r will become r inverse, or the angle will become the negative angle. So these are active rotations. But if the coordinate frame is changed and the vector is fixed, and you use a negative value of r or the inverse of r if it's a more complicated three-space rotation. So row versus column is different, active versus passive is different, and they're inverses. So we're almost there. That was a rotation in two-dimensional space, in a plane. We need to rotate in a three-dimensional space, not a two-dimensional space. And for this, there are many conventions. For the plane, it's pretty straightforward. There's just more or less one convention that I know of. But for the three-dimensional space, you could describe it in a variety of ways. And this is the way we're going to use, and it's used by a lot of spectroscopists. These are called Euler angles, and it's a specific implementation of them called the Rhodes convention. Let's say that we had a dipole coupling that we want to view. Like in the principal axis system, it's a dipole coupling. And let's say that the lab frame, we're just going to be talking about B naught. So each of those frames is more like a vector than really a three-dimensional space. X and Y don't make any difference for a dipole coupling. X and Y don't make any difference for the NMR experiment. They have no real meaning. It's just Z is unique. So if I'm going to rotate, we call it a uniaxial object, the dipole coupling. It really has only one axis. X and Y are equivalent. If I'm going to take a uniaxial object and go to a uniaxial frame, there's only one thing about that that's important, which is the polar angle. And in this convention, what I like about it is that the polar angle is like a centerpiece of the whole sandwich. Polar angle takes the old z-axis let's say we're moving from the red frame to the blue frame. Oh no, I see, there is a direction. So let's say we're moving from the blue frame to the red frame. That polar angle is beta in this three-step sandwich of rotation. And it takes z to z, the main axis in the old frame to the main axis in the new frame, through an angle beta. And sometimes in NMR, that's all you need. If you're talking about uniaxial frame of reference for the final measurement, like just B naught is unique, and you're talking about a uniaxial interaction that you're working with, sometimes you just need that one angle, even though it's three-space. So that's the centerpiece here. Move old z to new z, and by convention we call it angle beta. That's the polar angle. Now, What if X and Y were different for the frame? What if the interaction were like the CSA and X and Y is different on the molecule? Then a full description. If I want to describe something that has a shape and I want to place it just so in the final frame, what's all the information I might need? Here's the way I think about it. The first rotation that I'm going to do is to line my object up so that I'm sure that I have a y-axis, I'm going to call N here for node line. My y-axis is perfect for taking the old z to the new z. There's only one such axis, it is the mutual perpendicular. So if my object has some shape, I need to line it up so that z, new z and old z, and one of my coordinate axes, and by convention that's y, have this relationship that y is the mutual perpendicular of these two vectors. I might not start that way. My first axis might not be so convenient that my y-axis is exactly perpendicular to old z and new z. That's the rotation axis that I want to use to move z from its original position to its final position. So I might need to take whatever I'm given, which has y over here, and move that line to here, where it needs to be for that central rotation. So it's basically a setup for the central rotation. So I want to move the old y to a new y that's a mutual perpendicular, and that you can always do for any z and any old y. You can always rotate around. This is kind of showing that there's always this intersection. Doesn't matter where y was, you can always find an intersection point between this sort of perpendicular plane and this perpendicular plane, and that's where you want to move your y-axis to. So the very first step is azimuthal. In other words, you're not moving the polar axis at all. In fact, you're rotating around it to set up y so that y can move your initial polar to the new polar. So I think of that as a setup. I think of this as the major angle. And now, after I've done that, I do have a choice of maybe where would I like y and x to be. And most of the time it doesn't matter for NMR problems, but it might. We'll come up with an example where it does. So I've gotten z where I want it, and now I may need to twirl the x and y axes around until all they're perfect. So it's three angles. So one is azimuthal to set up the central rotation, which is polar, and then another rotation around z.
And are alpha and gamma in that figure drawn correctly, the angles? Because you're talking about y, but alpha and gamma both appear to be associated with x.
And you want alpha really to be between, this is the first axis and the node line. And I don't see why that would have to be equivalent. That's a good question, Mike.
Right, because alpha looks like it's taking x to the node line, not y.
This is my pet peeve, but I've done it myself. Instead of drawing my own figure, I took a figure that I thought was very elegant. And I'm always telling people to do that.
Right,
yourself, because you're right. For the convention I'm using, it may not be wrong for whatever they were doing, but for the convention I'm doing, it's misleading. You're right. Thank you, Mike. Okay. Other questions? I want to say the same thing in an equation. It's three operations. A rotation around z, a rotation around the new y, and a rotation around the doubly new z. So, and it's going to be a 3 by 3 matrix because it's a rotation that's going to act on a 1 by 3. In this case, I set it up as a column, but it doesn't have to be there. Okay, so what I need to do is to do it sequentially. First, I rotate about z through an angle alpha, then I rotate about y through an angle beta, and then I rotate about z through an angle gamma. And having done this problem in the plane, I think you can understand that this is the right way to rotate around Z. I don't mix Z with anything. If I rotate around Z, Z stays still. So it's the only entries on the column and on the row containing Z are on the diagonal. Z doesn't mix with anything. And then it mixes up X and Y just the same way as we did when we did the rotation in the plane. So having done the two-dimensional, you know that that's right for the three-dimensional. And then this is the same thing except for a Y-axis. If I don't mix, I'm rotating about Y, I don't mix Y with anything, and I'm doing projections for X and Z, and I follow it up with another rotation around Z. One thing you'll notice here is that we do a lot of Z rotations. So when I start to work with spherical harmonic basis set, the thing about it is it just makes Z rotations a lookup, just automatic, there's no work, there's no math to do, there's no arithmetic, literally there's none. So we're going to come up with a special coordinate system where Z rotations are literally a piece of cake. So this is our rotation, this is how we rotate things. And you can gang that all up and do the multiplication and you get this. If you're going to stay in Cartesian coordinates, you'll be doing this all the time. Now, I don't know about you, but when I do things like this in paper and pencil, I just end up with mistakes, and I do it 4 times, literally 4 times. To get to that agreement, I do it 4 times. And remember that there are 2 copies of this in our equation. We have to rotate I, and we have to rotate B. So we're going to look for simplifications. We're going to look for simplifications, how to do these rotations without doing all of that. And the simplification we choose will have to do with 2 things we know already. One is that we only want the sigma 3,3 element. We actually don't even need the rest of it. And number 2 is we're doing a lot of Z rotations. So given those 2 things going into it, there's really a best choice in terms of simplifying all this stuff, and it's the spherical harmonics. So we're going to use these. Basically, just to put it back into context, we're using it to do the following. This is the definition of B naught in the laboratory frame. This is the definition of I in a laboratory frame. Again, I really don't need to be using these 0 subscript. I think I should have left it out. So it's just the B field in the lab and the spin degrees of freedom in the lab. And what got messed up in the MAC to BC conversion is just it should have an arrow on top of it. It's a vector. So over here, where we were scratching our heads, we were saying, yeah, I can look this up from some JAX paper. I can get the shielding tensor in the principal axis system. The thing is, I don't know how to write I in the principal axis system. Well, this is how you do it. You construct that matrix, as long as somebody gave you the values for alpha, beta, and gamma. Construct that matrix, and you multiply it to get the magnetic field in the principal axis system. And same thing. And this looks a little different because this is a column vector. This looks like this because it's a row vector, but it's just that same vector that represents a rotation that we'll be using. So we have to put that all together to make this equation on the bottom, where we are allowed to go get sigma from someone else's paper in the principal axis system. We intuitively know how to write B and I in the laboratory frame. We have to construct these rotation matrices, so we have to be smart about what we think the angles are. This is a topic we'll talk more about later. It's a rotation in 3 dimensions for dipole coupling, CSA. We're going to use it for lots of different problems. Now, R is the thing that's time dependent. We think of sigma as more or less for all time. I mean, it's true that if something changed in your experiment, like a chemical reaction went on, or a conformational exchange that had a big effect on interactions, maybe the chemical shift values would change. It's true. But most of the time, we think that changes in the sample, like magic angle spinning, conformational exchange, what they're doing in terms of this equation is they're changing the value of R. That's what the time dependence is. It's in R. Most of it. So I want to just raise one more point. Is anybody here feeling uncomfortable that they needed to leave at 2:30 on the dot? Are you okay for like another minute? We started a little late. Sorry. So this doesn't have any frame. It's an energy. It doesn't matter which frame we picked. We picked the principal axis frame because we didn't know how to rotate this tensor, but we figured that we could argue our way through how to rotate a vector. And that was just taking us back a little bit to high school or something. I don't know, when did you do that? You guys are all from different parts of the world. When did you learn to rotate things? Was it middle school? Was it high school? Was it college? It's kind of geometry problem. High school, right? It should be high school. All right, so I'm just refreshing that for you. But this tensor, this is a 3x3. You ever have to rotate one of those? Yeah. So you can learn something by just looking at the solution. This isn't exactly a proof, but you could change it up a little bit and make it into a proof. This, we know, is in the lab frame by construction. This is in the lab frame. So clearly this sandwich here inside the box must be sigma in the lab frame. That's how you rotate a tensor. We call it bilinear because you have to put 2 copies of R to move it around. If I want to move sigma, it's a 3x3 tensor. It has 2 spatial indices, the index that says where am I measuring, and the index that says where was the perturbation. There's 2 indices, so it needs 2 copies of R. These 3x3 two-dimensional matrices need to be rotated by multiplying before and after by R, whereas the vector just needs 1 copy. And these 3x3 matrices in general, they can be thought of. There's a book written by Hans Spies called Rotations of Molecules and Spins, and he shows formally how you can make all of these tensors out of vectors, and it's always takes 2 of them to make a tensor. Combining 2 vectors to construct a tensor, each of those vectors needed to be rotated. The tensor needs to be rotated twice. So by doing that derivation that way, we just learned how to rotate tensors, and it's R inverse, and then the tensor, and an R. Now, what about these subscripts? PL, from the PAS to the lab. I didn't stop and talk about that subscript when I was doing these vector rotations. That was a passive rotation from the PAS to the lab. I'm sorry. The L here. For the vector, when I was working with the vectors, that's passive frame transformation, where we started out in the lab and we ended up at the PAS. That's the same as if it would be active from the PAS to the lab. Okay, those vectors are B and I. They start out in the lab frame and they're passively moved to the PAS axis. But here, for the tensors, the same rotation can be used for the passive transformation from the PAS to the lab. And that's the way we're going to think about it. All this is equivalent. You could say that that is the same particular values for R could be used to do an active movement of a vector from PAS to the lab, a passive from the lab frame to the PAS frame. But the way we're going to think about it is that we move the tensor. Because actually, if you did an experiment, you're not moving the magnet, you're moving the sample. So the natural way to think about it physically is that I'm moving the sample and I'm changing its frame transformation from the PAS, where I know how to write it, to the lab, not to the lab, okay? So that subscript PL, the way I unpack it, that I mean passive transformation from the PAS to the lab. RPL. But when we first introduced it, you could have said it was one of those other things. Now, the need for simplification, it's compelling. Not only was that one matrix kind of ugly, and not only do we have to have 2 copies of it for every single frame transformation, but think about this. We usually do more than 1 frame transformation when we describe an NMR experiment. I mean, that's kind of bad news, but it's true. In order to think clearly, you want to like do it in steps. So for example, maybe I want to talk about how the PAS of like some carbonyl and some amide relates to the long axis of the molecule. Or maybe I want to talk about how it relates to the crystal axis if it's sitting in a crystal. And there'll be structural information if I can take a bunch of those functional groups and move them all to the same common axis through different angles. So I'll be saying like this stuff in this alpha helix, it all has a beta value of 40. But down here in this sheet, most of these have a beta value of 20. That's structure. Get enough of those angles together, that's structure. So we take each functional group on its own, from its own PAS, and move it to a common frame. Maybe 100 of them or 200 of them going all the way through the protein. But now we're just in a crystal frame. We're not all the way to the lab frame, right? We're on a molecule frame or a crystal frame. And maybe we'll need both of those for some problems, but let's just say we choose. Either we're going to go to a molecule frame or a crystal frame. Now what if we're doing magic angle spinning? That molecule is moving during time when I rotate the rotor. I need another frame. I need a frame that moves with the rotor, and I need to make that molecule jump in to the rotor frame. Because I'm going to have a bunch of molecules like Avogadro's number, and they'll all have different relationships to the rotor frame. So I need an angle for that. So 1 frame transformation from PAS to the molecule. That's where structure information is hidden. Another one from the molecule to the rotor. That's your power averaging. That's your ensemble that you're building up, an homogeneous ensemble. Now I need to move the rotor to the lab. That's magic angle spinning. 3. And each one of them comes with 2 copies of R. Some of those R's are sample dependent, some of them are time dependent. I think you get my point that we need to simplify this stuff, like as in a lot. Even if I was just going to type it up and put it into Mathematica or MATLAB, I still want to simplify it. I don't want to just do it this way. Conceptually, this is the clearest way to explain what we're doing, but it isn't the way to do the calculation. Remember, again, no matter how many nested frames you have, most of the time, the time dependence in the experiment will be in those R, the rotation matrices. So we're going to be interested in simplifications, and in the notes, which we're following more and more, you can look ahead if you want, but tomorrow we're going to talk about Cartesian coordinate systems versus this special system called spherical harmonics. How are they related to each other? And what's so brilliant about spherical harmonics? Okay, that's what we're doing tomorrow. So introducing, defining spherical harmonics and talking about its virtues and why it's going to save us so much calculation. So please, if you have time, look at some of these questions that are in the notes or that I raised with you today during the lecture so you can come up with questions for tomorrow. I don't know if we'll do like formal homework tomorrow or not, but if you come up with questions, that would be better. Okay? Good.